from Clemson University who will be talking about infinitely many cyclic cubic fields with no units of mixed sign. So thank you, Ben.
Thank you, DCV. I just want to say thank you to the organizers for setting this all up. This is my first PANTS conference. I've heard a lot about them, but I've never been able to partake. And so it's really awesome to be down here and doing this. So today, I'm going to tell you a little bit about a fun result, which is something that I worked on where we ended up proving that there are infinitely many cyclic cubic fields with pajamas, yes. A fun result where we ended up proving that there are infinitely many cyclic cubic fields with no units of mixed sign. And so I'll explain what that means in just a sec. This is joint work with John Voigt, Elif Arma, and Noma Elkes. So just kind of a quick introduction to some of the ideas that I think about. If you take so we're going to take F to be a number field, and you can suppose that you have R1 real embeddings. We'll take OF to be the ring of integers and OF cross to be the unit group. And what you can do is you can define what's called a signature homomorphism. And so this is a map that's going to take a unit, and you're going to think about embedding the unit into each of the real places of your number field. And just looking at whether that element is positive or negative under each of those embeddings. So you're thinking about just taking a unit in your number field and then mapping it into the real numbers in all the different ways and just kind of recording whether it's positive or negative under each one of those real embeddings. We would say that a unit has mixed signature if the unit has both kind of like a positive image and a negative image in one of the embeddings. And a concise way of saying this is that the sign of the unit, the signature of the unit is not equal to the signature of plus and minus one. If you think about taking one and you embed it into all the real places, it's positive at each real place. You take negative one, embed it into all the real places, it's going to be negative in each one of the real places. And lastly, you can define what's called a unit signature rank. And so the idea here is that you can think about this space up here, this plus minus one to the R1, as really being a F2 vector space. And every element in there is a tuple of like pluses and minuses, so plus minus, plus minus, plus minus. And we can form this notion of like what is the kind of like the dimension of the image of these units in this space. So how many signs do we have? And we do this by looking at taking the signs of all units in our number field and then just taking their F2 dimension. And so we call this the unit signature rank. And this is a quantity which ranges from 1 to R1. So the reason that the lower bound is 1 is that every number field has a negative 1 in it. And negative 1 has non-trivial image inside that space. And so the former occurs. So when we have signature rank 1, that means that all our units are either totally positive or totally negative. So their signs are all the same essentially. And the latter occurs if you have units of all possible signatures. So the first thing that you might want to think about in terms of unit signatures is looking at like a real quadratic field. This is probably the simplest example that we can consider. And when you do this, you'll find that unit signatures are linked to a classical equation called the negative Pell equation. So this is of the form x squared minus dy squared is equal to negative 1. And when you think about the integral solutions to this equation, you'll see that the integral solutions correspond to a subgroup of units in the ring of integers. And these units will have mixed signature. The way that you can, so explicitly, I guess what I mean there is that if you think about having some integral solution xy, then you can map this to the point, to the element of your number field, which is x plus square root of d times y. And that's going to be a unit in the number field, and the unit is also going to have mixed signature because the norm is -1. So in one of the embeddings, that element is positive, and the other embedding, it's negative. So the negative Pell equation has been kind of classically studied, and interestingly enough, you'll find that the subgroup of units which satisfy the negative Pell equation is generated either by the fundamental unit or its cube. And so what you see here is that the solvability of the negative Pell equation will then be equivalent to whether your real quadratic field actually has a unit of mixed signature. If it has a unit of mixed signature, that's got to be the fundamental unit the fundamental unit will certainly have mixed signature. And that would mean that then the subgroup E of F actually has some solutions to it. And alternatively, if there is no units of mixed signature, then there's going to be no solutions to this negative Pell equation. So in short, the negative Pell equation can immediately tell you whether your real quadratic field has units of mixed signature or whether it doesn't, just based on its solvability. So you find from this, when you consider kind of very general real quadratic fields, you'll find that 100% of real quadratic fields will have signature rank 1. So the units all are either totally positive or totally negative. And to just kind of give a quick sketch of this idea why this is true, you start with considering that negative Pell equation, and you take a prime p, which divides the discriminant of your quadratic field. And if you look at this negative Pell equation here, you can think about reducing it mod p. And so when you reduce this mod p, you get something of the form x squared is congruent to -1 mod p. And when you think carefully about that, that means that you have an element x in fp such that that element is a fourth root of unity. And so, if you think about FP, you know that the multiplicative, every element in the multiplicative group of FP satisfies x to the p minus 1 is equal to 1. So these are p minus 1 roots of unity. So in order for FP to contain a fourth root of unity, it must be congruent to p, it must be congruent to 1 mod 4. So this would mean that if you looked at an arbitrary discriminant and you wanted to say, well, is there a solution to the negative Pell equation, you need to make sure that your discriminant is entirely comprised of primes that are congruent to 1 mod 4. Any prime that's congruent to 3 mod 4 would immediately obstruct a solution to the negative Pell equation. And when you start thinking about this asymptotically, you realize that, okay, if I have a really big discriminant, there's a lot of prime factors to that. And, for each prime factor, at least for the odd prime factors, you're flipping a coin. You're basically saying that, it's either 1 mod 4 or 3 mod 4. And you expect that to find discriminants that are all the primes are congruent to 1 mod 4 should be really, really rare. And so it should make sense that asymptotically 0% of fundamental discriminants have primes that are congruent to 1 mod 4. So that's a kind of a short sketch of why 100% of real quadratic fields will have signature rank 1. Is this Pell equation is kind of locally obstructed whenever you have a prime that's congruent to 3 mod 4. So the next simplest case to consider is you can move up and you'd say, what's the next kind of simplest Galois setting we could look in? And that's a cyclic cubic number field. And so when you think about cyclic cubic number fields, you'll realize that the unit signature rank of a cyclic cubic field is always 1 or 3. The reason for this is that if you have a unit that does have mixed signatures, say like plus, plus, minus, then the Galois group will act on that unit. And what it does is it actually permutes the signatures of that unit. And so you'll get something, if you start with plus, plus, minus, you'll kind of permute it and you'll get something like, what is it, minus plus plus or something. So you can quickly kind of see that if you have something with mixed signatures, you actually have all possible signatures. And really what's going on here is there's a Galois module structure on the units. And so we set out when we embarked on this project with John, my advisor, and Ela, is we wanted to kind of make some heuristics to, there's no theorems to tell us what unit signature ranks of cyclic cubic fields were. And so we wanted to produce some heuristics to try to tell us what we should expect for unit signature ranks of cyclic cubic fields. And we were able to actually support these heuristics pretty well with computational evidence, but our end result was that we conjecture that approximately 97% of cyclic cubic fields have unit signature rank 3, and approximately 3% of cyclic cubic fields have unit signature rank 1. So the idea being that if you arbitrarily kind of pick a random cyclic cubic field, you should expect that it'll have unit signature rank 3. So there are the full unit signature rank. There's units of all possible signs. So now these heuristics are interesting and they're a great point to kind of talk on, but I'm not going to do that today. What we wanted to do is we wanted to come up with some sort of theoretical backing for these heuristics. And so the first thing you might want to think about is like, can we prove that there is some like positive proportion of fields of cyclic cubic fields with unit signature rank 3, or positive proportion of fields with unit signature rank 1? And trying to do this, we really didn't make any progress at all. It's a very difficult question. And so we settled for just asking, can we prove that there are infinitely many cyclic cubic fields which have unit signature rank 3? Or conversely, are there infinitely many cyclic cubic fields which do have unit signature rank 1? And looking through the literature, we found that in 1974, Daniel Shanks established that there are infinitely many cyclic cubic fields with signature rank 3. So he found a one parameter family called the simplest cubic fields, and he showed that these fields, they all had unit signature rank 3. And this kind of agrees with what we would expect here. You know, we predict that 97% of fields have unit signature rank 3. So it makes sense that what had been found in the literature so far was an example of that. So the converse to this is like, do we know that there's actually infinitely many cyclic cubic fields with unit signature rank 1? And that's what we ended up proving in 2019, was we produced a construction which allowed us to explicitly write down cyclic cubic fields that had unit signature rank 1. So that's the main thing that I want to talk about today. I'm now just going to kind of quickly walk through a sketch of some of the ideas that went into this. So we started with an arbitrary a polynomial in the determinants a and b. So you can think about this as f of a, b. And this polynomial is x cubed minus ax squared plus bx minus 1. So, you know, if you think about taking two arbitrary integers a and b, plugging it in for the a and b in this polynomial, you would expect that, you know, generally speaking, this is probably defining, the roots of this polynomial would probably be like units in a cubic field. You might have something go wrong where, you know, it's possible that it would have like kind of this polynomial would be reducible over q. It might factor as like a linear term times a quadratic, but that's actually very rare. And if you're curious about when that occurs, you can actually classify completely the set of a and b for which that happens. And so for the purpose of this talk, we can pretend that this polynomial is going to be always irreducible. And so our goal is really, we want to try to find infinitely many integral pairs a and b, just to kind of start with. Find infinitely many integral pairs such that the roots of this polynomial are units in a cyclic cubic field. So the main thing to highlight here is we want the roots of this polynomial not to just be a cubic field, like an S. We want to make sure that it's actually a C3 extension, not an S3 extension. So we want it to be a cyclic cubic field. And we really want to find infinitely many integral pairs. So to think about this, one of the first things that I think is going to be helpful as I go through this talk is you can think about when you let a and b vary over the real numbers, you can look at the discriminant of that polynomial. And you can consider the discriminant as a function of the kind of over the AB plane. And so the discriminant is drawn right here. It's dAB equals this quantity given here. And you should have a kind of like a very strong geometric intuition in terms of discriminants. You'll remember that when the discriminant is negative, and that's this region right here, it's going to have the roots of your polynomial you'll have complex roots. And when the discriminant is positive, you'll actually have real roots. So particularly because we're working with cyclic cubic fields, the roots are always going to be totally real. And so we want to find integral points that lie in the region and this side or this side here. So the first thing that we kind of thought about was we said, okay, you know, if you want to write down an integral pair and you want to make sure that this polynomial actually defines a cyclic cubic field, you can go back to kind of Galois theory and you'll see that you can detect whether a cubic polynomial defines a cyclic cubic field or an S3 field based on whether the discriminant is a square. So when you look at this condition, you're saying that c squared is going to be equal to the discriminant of d of ab. And when you think about that carefully, you realize that that equation there actually defines a surface in R3. And so we can think about, instead of finding infinitely many integral points a, b, and c squared, we can now try to think about finding integral points a, b, c that lie on this algebraic surface. And so if you're curious what type of algebraic surface this is a log K3 surface here. So we updated our goal and we said, okay, you know, we no longer want to try to find infinitely many integral points a, b, and c squared, but we now want to try to parameterize some algebraic curves on the surface. And we want to make sure those algebraic curves actually contain infinitely many integral points. And so I should just kind of note a brief bit on the history of the surface is that we weren't really the first group to actually think about doing this procedure and to kind of play around with the surface. The first person that actually looked at this was Shanks, the simplest cubic field, which I mentioned earlier. So he found a curve on this surface, and when you map the curve back to the polynomials that I was describing, it corresponded to the equation x cubed minus ax squared minus a plus bx minus 1. And you can think about this, if you think about the AB plane, what this is really doing is you're setting b equal to negative a plus 3. And so that's just going to be a line in the AB plane. And the set of points satisfying the curve that he had found was all the integral points of the form a minus 3, a squared plus 3a plus 9 that lay on that surface. Another person who actually studied curves on the surface was Baladi, Steve Baladi in 2016, and he found several families of curves on the surface that contained infinitely many integral points. But unfortunately, those are rather hard to describe here, particularly in a 20-minute talk. So, and when we did look at these, the problem with both of these different families of curves on the surface was that we could pretty quickly tell that the roots of the corresponding polynomial that we had originally defined, this f of ab equals x cubed minus ax squared plus bx minus 1, actually had mixed signs. So the roots of that would have mixed signs, and so it immediately guaranteed that the unit signature rank was 3. And so the curves that existed in the literature weren't really any help to us. So we wanted to find curves such that the roots here were totally positive. And I know I said that when I gave this talk at Dartmouth, Carl Pomerantz immediately pointed out that it's weird to require the roots to be totally positive because you just really need all the roots of the polynomial to be positive, or you should say a root of the polynomial is totally positive. But the idea being, so if you do think about that discriminant and you're thinking about what happens in terms of the roots of the polynomial, you realize that the polynomial will have complex roots in this region here, which is this. Sorry, this is the graph of the discriminant, and in the AB plane, and then the roots will be real when you have points corresponding to this region here. And if we want to guarantee that the roots are totally positive, we want to look for roots in this region, in this kind of positive region of the AB plane right here. And that's just kind of some thinking about kind of continuity there. And you can make this a little bit more explicit if you do want to check, if you do want to kind of confirm that the roots of this polynomial will be totally positive when A and B are positive, you can observe that this polynomial will actually output negative values whenever you plug in negative values for x. And so you know that there's no roots when x is negative in that case. And so all the roots have to be positive. So to summarize what we were able to kind of contribute, which is new to the literature, is we found several families of what are called Fermat-Pell curves on the surface. And these Fermat-Pell curves, CM, were indexed by a rational parameter m. And these curves actually did contain infinitely many integral points. And to kind of briefly describe this, if we think about taking these curves and projecting them down into the AB plane, you're thinking about the curve, you have some surface up here and we've found some curves on the surface. And if you project them down into the AB plane, you'll find that the projection ends up being parabolas. The parabola is given by B is equal to some constant m times a quadratic in A. And on the parabolas, so if you think about taking one of these parabolas and plugging that into the discriminant equation, so physically, I mean, take this B right here and substitute this into our discriminant. After an appropriate change of variables, you can recognize this as a Pell equation. And so if you know stuff about Pell equations, I guess standardly Pell equations usually come to you with the form x squared minus d y squared equals n. But you can complete the square on the side of the equation to get a Pell equation. And if you know stuff about Pell equations, you know that there's two cases. One is when the discriminant is negative, in which case you're essentially working in an imaginary quadratic field, and there's only going to be finitely many solutions to the Pell equation due to the fact that there's only finitely many units for imaginary quadratic field. But if you're able to make sure that the discriminant of the Pell equation is positive, then you're working in a real quadratic field. You have infinitely many units, and given any solution to the Pell equation, you can multiply it by a unit to get to other solutions. And so this is how we were actually able to construct infinitely many points on these curves, was we could work with the corresponding Pell equation, find integral points on the Pell equation, and particularly infinitely many integral points in the Pell equation, and pull those back to integral points on our curves and on our surface. So just to kind of show you a picture of the Fermat Pell curves, here we have this is the graph of the AB plane, and here we have when the discriminant is equal to 0. So in this region here, if we plugged in points A, B into our polynomial f of x, then they'd be complex roots of that polynomial. But the region that we were interested in was this region right here, which I'd highlighted in baby blue earlier. And this region, when you plug in integral points A, B into the polynomial, we'll have the units will be totally positive. And so here's our orange curve, and you can see that it kind of runs along this region, and we'll end up finding infinitely many integral points along that curve there. And just to show another example, we have right here, I've illustrated in red, this is the simplest cubics that Shanks found way earlier. And you can see that that's actually on the wrong side. So it'll turn out that every integral, every point A, B that lies on this line right here, if you plug that into the polynomial f of A, B, you'll find that you have units of mixed sign. So I think that's just about, there's one or two kind of more cool things that I want to talk about, but I should probably just end here. I just want to say that this construction, what I've shown you so far, we found infinitely many ways to kind of produce units, totally positive units in cyclic cubic fields. And we have to do a couple more steps to actually say that the fields that we're producing are actually distinct, and that the unit signature rank is 1. And those are both really cool, really fun arguments, but I think with a 20-minute talk, I should probably end here. So I'll pause for questions.
First, let's thank Benjamin again. Not again, but the first time. Any questions for Ben? All right, I need to make you a co-host quickly. All right, you're unmuted, Guillermo.
Oh, so I have several questions, but maybe so. When you said there is some cool things to check if they are different, it doesn't have to be. It's related with the regulator. So the first thing that came to my mind was like, is it possible that the regulators in your parameterized examples are different?
Oh, that's a great question. And I think that's how Baladi proves stuff in terms of them. So when we actually looked at why there's infinitely many fields that are occurring, what we did was we were able to use Newton polygons to show that we were getting discriminants that were arbitrarily large for the fields. So we looked at looked at the polynomials locally.
Yes. Okay. So that was another question that I was gonna ask. Related to, because for the quadratic fields, or the heuristic argument that you gave for the 0% was sort of a local argument.
Yes,
but,
yes.
But then, so one wonders, like here, you're not like, you haven't done a local argument to what you like. So it's strange, and especially because you could, like, for these cubic fields, you could say like, let's say the tame ones, there is no wild ramification. Then those guys, the primes that divide the discriminant are just congruent to 1 mod 3 or something, I think. So you could say something like that, but no idea.
Oh, yeah. Okay, awesome. I haven't, we made this construction, and I was hoping this would be a fun problem for other people to think about, how do we parameterize curves on this really interesting surface? And we kind of just went with the first thing that came to mind was, we want to show that we actually are getting infinitely many fields. And it's helpful to remember that these points A, B are really coming from like a Pell equation. So the solutions grow super quickly. And so that's part of what's going on with it when we look at the Newton polygons, why it can quickly kind of show. Yeah.
That's very nice. I guess, yeah, the regulator, like if you calculate it, or like if you find examples, I mean, I would love to see an example of two cubic fields that have the same regulator.
Right.
but I don't think that exists. But that's just, I mean, I don't have any proof for it, but I'm very, if I have to bet some money, I would say the regulators are just one-to-one with cubic Galois fields.
Oh, okay, awesome. Thank you. Thank you.
Thanks.
All right, other questions? Brandon asked a question in the chat. I'll read it. If I understand correctly, you construct cubic fields with sign rank 1 by relating it to a certain quadratic field through a Pell equation. Is there a nice way to understand the connection between these fields?
Oh, oh, that's a good question. Yeah, so we do have, so I did start with kind of Pell equations for quadratic fields in terms of understanding unit signatures. And when we do find these, so when we do kind of find these parabolas here, which will, the discriminant turns into a Pell equation here, I haven't analyzed what possible quadratic fields are showing up. I mean, we do a lot of fiddling with this rational parameter m to make sure that the quadratic fields that we get are actually real quadratic fields, so they will have infinitely many solutions to the Pell equation. But I haven't actually analyzed too much what Pell equations are showing up. So that would be a good thing to look at. Are there other families of curves that might pass through the totally positive region? We haven't, I don't know. That would be really cool if someone else could find a family of curves that passes through this region where the roots will be totally positive. We searched kind of long and hard for them, and we started with kind of like, very simple kind of like linear curves, something like the Shank's simplest cubics, and then we moved up to quadratic because we couldn't find any that were linear. But yeah, I'd be really interested to know if there is like higher dimensional curves that might.
So they're not common.
I don't think so. As far as I can tell, all the people that have considered the surface are Shanks, Ballady, and us.
Thanks.
Yeah.
I have a question about the quintic, or at least the heuristic in the quintic case.
Oh, for
for
our heuristics?
Yeah, I've seen John talk about this too. I'm
okay.
just curious.
99%.
Well, I have a weird question. In those cases, you're still looking at the case where you have, at fields where you have the maximal number of real embeddings.
Mm.
What if in those cases you do something mixed? So if you look at quintic fields where you have 3 real embeddings and then a pair of complex conjugate.
Right.
Is there some, do you get a heuristic there as well?
Yes. So there's 2 things going on there. So for a cyclic, so if you do look at a cyclic quintic field, it's Galois, and it automatically has 1 real embedding. So actually all the embeddings are real. And so that's why we only considered the case with all 5 real embeddings in that case, and that's the 99%. But your question can also be asked for what happens to like an S5 quintic field. And John actually did make heuristics with Dave Dummett in that case. And yeah, so that's a very interesting. And John's, yeah, the reason we're doing this is, there's a fundamental exact sequence in class field theory that links units and unit signatures to Ray class groups. And so that's what we're after at the end of the day, is heuristics for Ray, Cohen-Lunsford type heuristics for Ray class groups. So yeah, thank you.
All right, let's thank Ben again.